So in chapter 4.1, we're going to look at association and correlation. So this is chapter 4.1. So we're going to be looking at bivariate data. That means two variables that are quantitative. So there are two quantitative variables. And we're going to look at the relationship between those two variables. And to do that, we're going to first construct scatter plots to look at the relationship between the two variables, which are going to be x and y. We're going to compute something called a correlation coefficient, and we're going to interpret that correlation coefficient. And then we're going to try to understand the difference between correlation or association and causation. So our first objective is to construct scatter plots for bivariate data or two variable data. So suppose that a real estate agent wants to study the relationship between the size of a house and its selling price. Is it reasonable to suspect that the selling price is related to the size of the house? Specifically, we expect that a house with larger sizes are more likely to have higher selling prices. So we're trying to look at the relationship between price and size. A good way to visualize the relationship with this is with a scatter plot. In a scatter plot, each individual in the data set contributes to an ordered pair of numbers, an ordered pair, x and y. Right? So we're going to look at x and y. So in our example of the size in square feet to the selling price in thousands of dollars, we have the following data set for houses in Denver neighborhood, and it says construct a scatter plot for the data set. So one thing we have to determine is which is our x variable and which is our y variable. Well, x is a random variable that is not dependent. It's an independent variable. So in this case, we're going to let x equal the size of the square feet. The selling price is going to be our y variable. Y is dependent on x. In other words, our selling price is dependent on the size of the house, not vice versa. We call the x variable the explanatory, and the y variable is equal to the response. So here's our x variable, size in square feet, and for each ordered pair, we will plot a point. So in the first ordered pair, we have 2521 feet, and it's worth $400,000. Right? In the second pair, we have 2,555 feet, and its price is 426. So these are what's called ordered pairs, and we plot each point within the xy axis. This is called a scatter plot. So we enter the data. In L1 will be our x variable, typically, and L2 will be our y variable. So we put those into our stats key and hit enter, and we put the data in. That's step one. We enter the data into L1 and L2. Then we press second Y, which is where our plot capabilities are, and we choose the first icon. Notice that we put in the X list, we put L1, and for the Y list, we put in L2, and then we just put a square for the mark. Well, in most cases, you want to set up the window key to allow you to scale the graph. So what that means is when you hit the Windows key next to the Y equal key, you can scale the graph based on the maximum and minimum values. Minimum and max values for X and Y. And we'll show this in class as well. Once you're done setting up the scale, then you press graph, and you end up with a screen that looks like this. So there's your scatter plot in the TI-80, 84 or 83. So now we want to interpret something about the scatter plot. In this case, we observe that the larger sizes tend to be associated with larger prices, right? So as the price increases, or actually in this case, as the size increases, the price increases, right? We refer to this as positive association between the size and the selling price. In addition, the points tend to cluster around a straight line. We describe this by saying the relationship between the two variables appears to be linear. Appears to be linear. And therefore, we can say that the scatter plot exhibits a positive linear association. A positive linear association between the size and the selling price. Well, association comes in various types. We will be discussing more of those types in class, but for linear data, it's usually two different types. One is a positive linear association or a negative linear association. If the data follows some sort of linear pattern between X and Y, we can see that in these two cases we have some sort of a linear association. There are other types of associations as well, ones that are nonlinear in association. And in those cases, we will see that the pattern of the data, there's an actual pattern for X and Y, but they're not in some fashion linear, right? Two variables that have linear relationships tend to cluster around a straight line when plotted on a scatter plot. Our second objective is to compute the correlation coefficient. The correlation coefficient is going to be represented by a symbol R, and in fact this R value is only going to be usable if we have linear association. So R is only going to be a good calculation if we have linear association. Well, this chart looks a little complicated. You do not have to memorize this information. We're just going to try to show you what the math is for the correlation coefficient, and we're going to try to make it as easy as possible. A numerical measure of the strength of the linear relationship between two variables is called the correlation coefficient, and we represent that correlation coefficient with the symbol R. Given the ordered pairs x and y with a sample mean x and a sample mean y, a sample standard deviation Sx and Sy and sample size n, the correlation coefficient R is given by this formula here. Looks complicated, but really what it is R is just 1 over n minus 1 times the sum of the z-score values of x and y. So that's really kind of a simple idea in some ways. We're going to do this calculation on the TI-83 or 84 and also on Excel, and typically we would not do this by hand. But we do want to show you how it is calculated. So here are the properties for R. The correlation coefficient is always between -1 and 1. That is, R is greater than -1 but less than 1 or equal to. The correlation coefficient does not depend on units of the variable. It does not matter which variable is x and which variable is y. However, when we're doing the interpretation, it does matter which variable is x and which variable is y. The correlation coefficient only measures the strength of the linear relationship. That's the only thing it can measure. It cannot measure association. So the correlation coefficient is sensitive to outliers and can be misleading if outliers are present. And we'll deal with that in Chapter 4.3. So going back to our original example where x values is the size of the house and y is the price of the house, we will compute the sample means and standard deviations. Here they are. Okay? And once we have those pieces of information, we're now going to compute by hand the correlation coefficient. So in the old days, when we had to do this by hand, we had to set up a table. And essentially, our first table was x, and this was the size of the house. And then we had the variable y, and this variable was the price of the house. And the second one, this was called zx. So each value represents the z-score value for x. Here's the z-score value for y. Well, how did we get the z-score values? Well, the z-score values are these equations. And finally, what we did is, in the last column, is we multiplied the z-score values of x times the corresponding z-score value for y for each of the ordered pairs. Finally, we summed up this last column. That last column goes into the numerator, and then we divided it by the sample size minus 1. So in this particular case, our correlation is 0.90, right? And it's close to 1, which means that we have a positive linear association. So we are going to show you how to do the TI-84 calculation to find the R of the correlation coefficient on both XL and the TI-84. Basically, to do this, you make sure that you've entered the data in to L1 and L2. You go to the calculate key, and you move down to option 4 under the calculate, and that option is called linreg, right? And there's a formula that says AX plus B. That's the option you choose. And then you choose, when it comes up on the screen, you'll choose L1, L2, right? And you hit enter. There is one other piece that you have to understand, is you have to make sure that the diagnostics on setting has been put on. And we'll show you how to do that in class. Once you hit the L1, L2 and you hit enter, you will get this screen here. And then, of course, in this case, R is the case. For the XL, in one of the columns, you'll put in the X variable. In the other column, you'll put in the Y variable. And in one of these cells underneath, you can hit the equal sign and type in coral, parentheses, A2 colon A9, comma, B2 colon B9. What's that doing? It's taking this array in the A portion of the formula, and it's taking the B part of the array in that part of the formula, and when you hit the little check mark above, you get this calculation for correlation. And again, we will show that to you in class. Well, now we're going to interpret the correlation coefficient real quickly. So the major ideas of interpreting correlation as follows. If R is positive, right, the two variables have a positive linear association, but here we have to be careful what we mean by positive. If R is negative, the two variables have a negative linear association, or somewhat. If R is close to 0, the linear association is weak. In fact, if R is 0, typically we don't have any linear association. No linear association at all. If it's closer to 1, it's pretty strong linear association. If it's closer to negative 1, it's more strongly negative linear association. So if R is equal to 1, it's exactly a straight positive line. And if it's negative 1, it's exactly a negative slope, negative line with negative slope. Okay, so those are important ideas. Typically, if R is less than 0.5 or is as it gets closer to 0, it's very weak linear association that can happen. So the idea here is R is only talking about the linearity of the data set. And sometimes our data set has other patterns to it that are not linear. So just because we have two variables that we can plot on an X and Y axis doesn't mean that we can make any sort of interpretations that is meaningful. So even though we may have a high correlation between x and y as a variable, it may not mean very much to us. And so here, correlation is not the same as causation. In fact, understanding association is not the same as causation. So here's a real ridiculous idea about correlation and causation. Suppose a group of elementary schools took a vocabulary test, and it turned out that children with larger shoe sizes tended to get higher scores on the test, and those with smaller shoe sizes tended to get lower scores. As a result, there was a positive correlation between the vocabulary and the shoe size. Does this mean that learning new words causes one's feet to grow, or that growing feet causes one's vocabulary to increase? That's kind of a ridiculous scenario. And so there is no causation, even though maybe the data shows there is a relationship. So the fact that the shoe size and the vocabulary are correlated does not mean that changing one variable will cause the other one to change. So in general, when two variables are correlated, we can't always conclude that changing one value of the variable will cause a change in the other values of the variables. We have to take it into context of the problem and see if in fact there is some sort of true relationship that is meaningful. So what you should have gotten out of this section is know how to construct and interpret scatter plots, know the difference between positive, negative, linear, and nonlinear associations. In other words, those data sets where there is a pattern but it's not linear. And finally, or the next two, is how to compute and interpret the correlation coefficient and know the difference between correlation and causation. This concludes chapter 4.1. Our next lecture will be on calculating a linear line equation for the scatter diagram that we have found.